The manufacture of parts by sintering powder compacts is one of the fastest growing production methods in the industrial world today. It offers unique advantages in economic shape forming and is applicable to virtually any material derived from a mineral source which can be prepared in a free-flowing form. Such materials include metals, metallic oxides, carbon, clays and glass. Powder compaction is probably the most critical part of the process, since this is what determines the form, dimensions and quality of the fired component. No matter how precisely the firing cycle may be controlled, the kiln cannot produce a good sintered part from a poorly compacted powder blank. Isostatic pressing techniques are now widely used to produce complex parts of more even consistency and density than are possible by other conventional methods. Isostatic pressing permits accurate formation of internal shapes, both plain and complex. It can reduce the need for drilling or turning and save valuable material. The easiest way to explain isostatic pressing is to take the example of a bathysphere deep down in the ocean. Water pushes it with enormous force from all directions at once. An isostatic press reproduces the conditions found several thousand feet below the surface of the ocean in compressing any object placed within it. In this case, the hydraulic pressure is generated by pumps and so can be accurately controlled. Dry bag pressing has developed the isostatic principle for high output production. Essentially, this has been achieved by using a tool set which consists of matching steel and flexible components. This is in fact a custom-made tool set and pressure chamber for a particular compact. When sealed inside a pressure vessel, the tool set becomes an integral part of the system. At the center of the isostatic pressure vessel is the preformed flexible mold. It's designed to form a blank or piece part. A membrane is used to keep the flexible mold dry, and this assembly is contained within the pressure vessel. Top and bottom sealing caps in the form of the tooling are positioned to retain the mold assembly securely in the vertical plane. A pre-machined mandrel may be inserted where a compacted part requires an accurate bore form. A measured amount of powder is fed into the cavity over the mandrel. When the cavity has been filled, the top tooling comes into place to seal it. Fluid is pumped around the flexible mold assembly and is pressurized. As the pressure increases, the loose powder is compacted into a solid shape. The amount of compaction depends on how much pressure is applied and the type of powder used. After a few moments, the pressure is released in a controlled manner. This speed of decompression is changed to suit different materials and compacted shapes. The loose, free-flowing powder is now a solid-shaped compact with a uniform density throughout. Let's look at that again. The pressure is built up, allowed to dwell if necessary, and then carefully decompressed. The flexible mold moves away from the compacted part and resumes its original shape, ready for the next cycle. When the pressure is zero and the bag has totally regained its shape, the compact can be removed. The top tool is moved upwards in preparation for the next fill of powder, and the bottom tool is moved downwards, taking the compact with it. The compact can be removed from the tooling before it returns to the pressure vessel for the next cycle. The powder is the key part of the whole process. It must be able to flow quickly and evenly into the cavity. If it does not, the compacts will have inconsistent weight and dimensions. Worse still, if the powder clogs or bridges on the way into the cavity, no compact will be produced. Different powders will compress by different amounts, resulting in different sized components. Depending on the natural characteristics of the powder, there may be a need to add binding agents to increase the component's strength after pressing. Today, dry bag isostatic presses are built in a wide capacity range, for laboratory use through to high volume production, with consistently high quality compacts. Technical backup is readily available in the form of advice on their application, tooling to realize this potential, and practical help to overcome any initial difficulties. The products for which isostatic compaction is used are probably more diverse than many people realize. As more and more engineers learn to appreciate its potential, new applications for isostatic pressing are being researched continuously to produce ever-widening ranges of different products.